Welcome back to the Deep Dive, where we take a massive stack of sources, articles, research, technical papers, and give you the distilled knowledge you need to be immediately well-informed. Today, we are undertaking a deep dive into what is really the engine of modern technology, machine learning.
It really is. It's a field that has completely, redefined how businesses operate and how we all interact with technology. To kind of set the stage, machine learning, or ML, is basically a critical subfield of artificial intelligence. It's the application and really the science of building algorithms that can learn patterns and derive knowledge directly from data.
And the reason this is so critical right now is the sheer volume of fuel that's feeding that engine. Our sources just hammer this point home, that we are basically drowning in data.
Right.
We saw one incredible statistic. Approximately 2 megabytes of data are created per second per person on the planet. I mean, that's just staggering.
It is, and that's more than just a big number. It's a fundamental technological challenge. This massive, chaotic flow of, structured databases, unstructured text, images, sensor readings, that's the environment that created the need for ML in the first place. Humans simply cannot process data at this scale.
Right. So our mission today is clear. We want to understand the mechanisms, these self-learning algorithms that can take that immense, overwhelming ocean of information and, well, transform it into knowledge. Knowledge that results in reliable predictions or these incredibly useful automated systems. Okay, so let's unpack this. I think the best place to start is just grounding it in reality.
Yeah.
Where is ML already operating in our lives, maybe without us even thinking twice about it?
Oh, it's truly ubiquitous. You mentioned spam filters, for example. That's a classic case of classifying emails as either, benign or malicious. Web search rankings, recommendations on Netflix or Spotify. These are all ML models working hard in the background.
And the digital assistants. Siri, Alexa.
Absolutely. The core technology behind assistants like Siri or Google Assistant relies on really sophisticated ML for natural language processing for understanding your intent.
And then you have the really high-stakes applications. I mean, things like intrusion detection systems that monitor network traffic for security threats. That's all ML. And of course, the whole revolution of self-driving cars from Google, Uber, Tesla. I mean, they're entirely dependent on ML systems interpreting this incredibly complex real-time sensory data.
Yeah, and what's particularly fascinating to me is how ML is now accelerating human capability, not just automating, basic tasks. The sources highlight some powerful breakthroughs that would have sounded like science fiction just a decade ago.
Like what?
Think about medicine. There was that major Nature article detailing how certain ML models can achieve parity with, or even surpass, human dermatologists in detecting skin cancer from images.
Wow. That immediately shows you the massive social impact these systems can have.
Exactly. And on the pure intelligence side of things, you look at DeepMind's AlphaZero, it's just an incredible story. This system was given the rules of chess, Go, and shogi, that's Japanese chess, and absolutely nothing else. No human games, no opening strategies.
Just the rules.
Just the rules. It played against itself, learned, and within hours, it defeated the strongest human and pre-programmed champions in the world. It just showed this extraordinary capacity for rapid abstract skill acquisition.
So that's the impressive what these machines can do. Now, if we really want to be informed, we have to look behind the curtain at the how.
Yeah.
We need to tackle the three main pillars, right? The three ways these systems actually learn.
Yes, and these three types, they really define the entire universe of machine learning. They're categorized by the kind of data and the guidance the algorithm gets from the human programmer.
Okay, so the first one, and probably the most familiar, is supervised learning. And it's called supervised because we're essentially acting as the teacher, right?
That's a perfect analogy. The goal is to learn a predictive model from labeled training data. We feed it examples, pictures of cats labeled cat, pictures of dogs labeled dog, and the machine learns the association so that when we show it a new unlabeled picture, it can make a confident prediction.
And supervised learning has two key applications.
It does. The first is classification, where the machine predicts a fixed, discrete class label. Binary classification is the simplest. You're predicting one of two outcomes, spam or not spam, malignant versus benign for a tumor.
But it gets more complicated than just a simple yes or no.
Oh, certainly. It scales up to multi-class classification, where the choice is between many defined outcomes. This could be classifying different types of security threats, adware, ransomware, trojans, or identifying the stage of a disease, like cancer stages 0 through 4. The machine is always choosing from a predefined set of buckets.
Okay, so if classification is about choosing a bucket, the other major type of supervised learning, regression, That's about finding a precise point on a spectrum.
That's a great way to put it. Regression predicts a continuous outcome. It's not choosing a label, it's predicting a value. Think about predicting the future price of a stock, or the sale price of a home based on its features, or even continuous variables in weather modeling like wind speed or the exact temperature tomorrow.
Right. I always visualize that classic example of, plotting points on a chart and trying to find the straight line that best fits,
Yeah.
that minimizes the distance to all the points. It's trying to predict where the next data point on that continuous line should logically fall.
Exactly that. That visualization of minimizing the error to the line, it perfectly encapsulates the goal. So now, moving away from labeled data entirely, we get to the second pillar, reinforcement learning.
This is where we stop giving the machine direct answers and we start letting it explore. This is the technology behind AlphaZero, isn't it?
It is. The goal of RL is to develop an agent that improves its performance based on interactions with an environment. It's all trial and error, much like how humans or animals learn. The core of the system is the reward signal, which can be positive for a correct action or negative for a mistake.
So the agent is basically just trying to maximize its cumulative reward over time. It's trying to find the optimal sequence of actions to achieve a long-term goal.
Precisely. And this approach is incredibly powerful for complex sequence decisions like training robots, automated trading, or, as we saw, mastering competitive games. The trade-off, though, is that RL systems typically require massive amounts of data and computational resources to explore the environment enough to find that optimal path.
Okay, that leads us to the third pillar, unsupervised learning. So if supervised learning uses labeled data and reinforcement learning uses rewards, what if we have neither? What if we just have data with a completely unknown structure?
That's the domain of unsupervised learning. The algorithm is dealing with unlabeled data, and its job is to extract meaningful information or patterns or hidden structures without any human guidance on what it should be looking for.
So it's purely exploratory. What's the main technique we'd use here?
The most common is clustering. This involves finding natural or meaningful subgroups, the clusters in the data. Imagine you give an algorithm a massive database of customer transactions and demographic data, and it groups them into 5 distinct, unnamed purchasing personas. The algorithm discovers those groups all by itself.
Interesting. And you mentioned that unsupervised learning is also key for data compression.
Right, that falls under dimensionality reduction. When data is huge, it often contains redundant or irrelevant features. DR techniques compress the data, which is useful in 3 key ways. It reduces the memory and CPU time needed to train a model. It can sometimes improve predictive performance by clarifying the signal. And it reduces noise by getting rid of those highly correlated or irrelevant features. It makes the dataset both cleaner and more manageable.
This is where we really move from the abstract to the tangible, because no algorithm can run unless the data is structured correctly. If you're building an ML system, what does the fundamental language of that data actually look like?
It all comes down to the 2-dimensional matrix, basically a grid of rows and columns. This is the foundational structure for most ML algorithms. We need to remember that every row in that matrix is a sample or a single observation, a single instance.
And every column is a feature, which we also call an attribute or a covariate. Let's make this really concrete with the famous iris dataset, which is, it's mentioned in nearly every foundational ML source.
The iris dataset is perfect because it's so simple. It contains 150 unique flowers from 3 distinct species, Setosa, versicolor, and virginica. And crucially, it has only 4 measurements, 4 features: sepal length, sepal width, petal length, and petal width.
So the matrix is 150 samples by 4 features. If I look at row 75, I'm looking at all 4 measurements for the 75th flower. If I look at column 3, I'm looking at the petal length measurement across all 150 flowers.
Precisely. And understanding that matrix lets us lock down some essential terminology we need. In supervised learning, the result we're trying to predict, in the iris example, the flower species, that's called the target.
And that target has a bunch of names, right? Outcome, class, label, but I think most importantly, the ground truth. That's what the model is striving to replicate.
Yes. And how do we measure the difference between the model's prediction and that ground truth? That's the job of the loss function, which is also called the cost function or the error function. The machine learning process itself is, in essence, an extremely complex optimization process aimed at minimizing the value of this loss function.
The lower the error, the better the prediction. Before we jump into the workflow, I just want to pause and note, if any listeners are inspired by the iris example and want to start exploring, the sources mention some fantastic public resources, places like the UCI Machine Learning Repository, Kaggle public datasets, and Hugging Face. They all have tons of foundational data to play with.
Great resources. Okay, so now let's talk about the practical roadmap. You've got the data, you've chosen your algorithm type. What are the actual steps involved in building and deploying a functioning ML system?
The first critical step, and this often takes the most time and effort, is pre-processing. Just getting the data into shape. Raw data is messy, it's inconsistent. What are we actually doing here?
We're converting that raw data, which might be text, images, huge JSON files, into those consistent, standardized feature vectors, like the sepal and petal measurements in our iris example. But the most critical challenge here is scaling.
Why is scaling so crucial? I mean, why can't we just use the numbers as they are?
Because the algorithms, they treat all features equally in their calculations. So if one feature is measured in millions, say the total salary of a person, and another feature is measured on a scale of 1 to 10, like a customer satisfaction rating, the salary feature will mathematically dominate the entire learning process. We scale features, typically into the range of 0 to 1, so that all attributes contribute proportionally to the model's learning.
That makes perfect sense. Otherwise, the biggest number just wins. And pre-processing is also where we deal with redundancy, using those dimensionality reduction techniques we mentioned earlier.
Exactly. Features can be highly correlated. If you measure a customer's age and their years of employment, those are likely so intertwined that including both just adds noise and complexity without really increasing predictive power. This is where we apply feature selection and dimensionality reduction to simplify the problem.
Okay, so once the data is perfectly clean, it's scaled. The next logical step is the training data split. We can't use all the data to teach the model, can we?
Absolutely not. You must split the data set into at least two parts. The training set, which the model learns from, and the testing or validation set, which is reserved specifically to evaluate how well the model performs on data it has never seen before.
We're making sure the machine isn't just memorizing the training data. And if a data set is scarce, the sources noted that techniques like stratified cross-validation like tenfold become essential to ensure a robust, unbiased evaluation across all the available samples.
That's a key technique for scarcity, yeah. Next comes the challenging phase, training and selecting the model. We know there's no single best algorithm, they all have inherent biases, so what's the reality here?
In the real world, you can't just pick one algorithm and be done. You have to compare a handful of different, often competing algorithms to see which one is best suited to your specific problem's data structure.
And you compare them using predefined metrics like accuracy, the proportion of correct predictions. But even once you select the best algorithm, the job isn't finished because you have to fine-tune the system settings.
The hyperparameters. Why are they such a difficult challenge for the human developer?
Well, hyperparameters are essentially the knobs that control the algorithm's learning process, but they aren't learned from the data itself. They're set before training even begins. Deciding on the optimal learning rate or the complexity of a decision tree is often a matter of educated trial and error. If you set them poorly, the model might overfit. It memorizes the training data perfectly but fails catastrophically on new data, or it might underfit, meaning it never learns the patterns at all. That fine-tuning step is often more of an art form than a science.
That sounds like where a lot of the time is spent. So the final stage is evaluation and prediction.
That's where the best performing fine-tuned model is evaluated against the completely untouched testing data to estimate the generalization error, basically how badly the model will fail in the real world. If the error is acceptable, the model gets deployed.
And there's that crucial constraint during deployment that we have to remind the listener about.
Yes, this is so important. When new real-world data instances come in, they must be transformed using the exact same scaling parameters and dimensionality reduction methods that were applied to the original training data. You have to maintain consistency through the entire life cycle of the model.
That entire complex workflow, it's almost always executed in Python, which is just the dominant language in the ML space. What gave Python the edge?
It's really a combination of community, speed, and ecosystem. First, the massive active developer community ensures constant support and library development. Second, speed is key. Even though Python itself is an interpreted language, crucial data science libraries like NumPy and SciPy use underlying Fortran and C implementations. This allows for extremely fast, low-level operations.
So Python gives you the readable high-level code, but the performance-critical calculations are actually running in much faster languages underneath the hood.
Exactly. And third, the ecosystem is just unmatched. It's home to the popular open source algorithm library scikit-learn and the industry standard deep learning frameworks like TensorFlow and PyTorch.
So what does this all mean for you, the learner? We've taken this deep dive and we've established that machine learning is, fundamentally, about teaching systems to derive knowledge from data by spotting patterns and making predictions.
And if we connect this back to the bigger picture, we highlighted that the majority of high-impact ML models, like the ones detecting cancer or filtering spam, they rely on supervised learning. They learn from labeled data categorized by humans. So the model's knowledge is entirely limited by the quality and the impartiality of the ground truth we provide it.
So the system is only as good as the human labeler.
Which raises a pretty potent thought for your own critical thinking. If the machine's predictive power is shackled by the assumptions and labels embedded in its training data, what are the inherent biases or blind spots in your own learning process? The one that relies on previously labeled, predefined knowledge. When you consume information today, are you questioning the label or just accepting the prediction? That's something worth mulling over.